Now that we have the Laplace equation in 2 dimensions, we can play with different boundary conditions. So first, let's think about how to handle non-homogeneous Laplacian. As a general statement, it works as we did with ODEs. We're going to be constructing a Green's function and then use some sort of convolution with the Green's function and the right-hand side. But this is a material for the next semester. As for the ODEs, the first step is to solve for the homogeneous equation. And this is the step we're going to be doing this semester. So we want to solve for the Laplace equation on a rectangle 0 to a times 0 to b. And we're giving Neumann boundary conditions. So Neumann boundary conditions on the rectangle are easier than Neumann boundary conditions in general, because what we have for Neumann boundary conditions is that you have the nabla of your unknown, u, times the outward pointing normal. For the rectangle, the normal has only one non-zero component. So when we are looking at the two vertical sides of the rectangle, the only non-zero component is the one associated with the derivative in x. When we are looking at the two horizontal sides of the rectangle, then the outward normal is the one associated with the y derivative. So as you see, Neumann boundary conditions in the rectangle are just applying some conditions on either the derivative with respect to x or the derivative with respect to y. And what we do when we have this two problems combined, so we're having non-homogeneous Neumann boundary conditions on all four sides of our rectangle, we split into easier problems. This is a great advantage of having a linear PDE to be solving. We can always split into easier problems, and we can choose the easier problems as long as, summing it up, we succeed in reconstructing what we wanted. This is fine. And the two easier problems we're going to be solving are the ones that associate trivial Neumann boundary conditions with respect to x and trivial boundary conditions with respect to y. By this I mean that we're going to be solving for v that satisfies the homogeneous Laplace equation with trivial Neumann boundary conditions on the two vertical sides of the rectangle and non-trivial boundary conditions on the two horizontal sides of the rectangle. And for the non-homogeneous, we pick exactly the same as the one for the full problem. And then we're going to sum this solution to the solution of another problem that is, again, the Laplace equation, the homogeneous Laplace equation. But now we swap which boundary condition we have chosen. So we keep the two Neumann non-trivial boundary conditions on the two vertical sides of the rectangle and replace trivial Neumann boundary conditions on the two horizontal sides of the rectangle. Now you see how when we are doing separations of variables for v and for w, we have one direction in which we have trivial boundary conditions and the other in which we don't. So let's look a bit in depth how it happens. Let's look at v, for example. You see that if you go on the horizontal axis, you go from a trivial boundary condition on one side to a trivial boundary condition on the other. Then we can apply separations of variables. And as we did before, we're going to be writing x second divided by x equals minus y second divided by y equal plus or minus k squared. I haven't chosen the sign yet because I want to choose that sign in order for the Sturm-Liouville problem to be in the correct form. So looking at the boundary conditions, we have trivial boundary conditions on the x direction. So when we want to impose a Sturm-Liouville form, we want to retrieve x second plus k squared x equal to 0. That is the direction in which we have trivial boundary conditions, so in which we can retrieve a Sturm-Liouville problem. That means that our k-squared in the separation of variable formula needs a negative sign. Then we have a Sturm-Liouville problem, and we have to be careful with which boundary conditions we are choosing. So here, I actually made a mistake because copying from one slide to the next, I dropped the fact that on the left side, there was a derivative with respect to x that should be written. So be more careful than what I have been. With this problem that I dropped the derivative, let's continue either way. We have a Sturm-Liouville problem that is x second plus k squared x equal to 0, and trivial boundary conditions on the two sides. One without the derivative because I forgot the derivative, and the other with the derivative. So we have x at 0 equal to 0 and x prime at a equal to 0. So now we know how to solve this. This is a Sturm-Liouville problem. It is in the correct Sturm-Liouville form. So we can write x, capital X, function of small x, as a sum of cosine and sine. So in the form a cos kx plus b sine kx. We haven't determined the value of k yet. So by imposing the boundary conditions, we have that at 0, x of 0 is equal to a, and we impose that equal to 0, so a is equal to 0. And then we have x prime at a equal to bk cos ka, and that also should be equal to 0. Either we have k equal to 0, and then we have the trivial solution, so 0 is not an eigenvalue, or we have cos ka equal to 0, in which case k is this multiplication of 1 over a times pi half plus n pi, where n needs to go from 0 to all the natural numbers. Why is 0 included in this case? Try to check and think about what different formulas would or would not include 0. Let's look a little bit more why k is n equal to 0 is included here. If we write k as pi over 2 plus n pi times 1 over a, then n takes the values 0, 1, and so forth. But we can also define k as n pi minus pi half times 1 over a, in which case n goes from 1, 2 to infinity. These two formulas and these two choices of n define the same set for k. So you have to be careful which of the two you're using in order to associate it with the right indices. Either ways, this allows us to find the eigenfunctions of xn that are sine k and x with associated eigenvalue lambda that is kn squared. Then we can solve for yn. What does yn solve? Where getting rid of some negative signs is yn double prime divided yn equals kn squared. So we can solve this. We know the solution is something we can solve with the characteristic equation. So we retrieve yn being a sum of hyperbolic cosine and hyperbolic sine. So specifically, we have some coefficient Cn times the hyperbolic cosine of kny plus some other coefficient dn and the hyperbolic sine of kny. You can write it as exponentials, but because we have boundary conditions at 0, sometimes it's easier to write it as hyperbolic sine and hyperbolic cosine because the hyperbolic sine at 0 is equal to 0. So now we can write the full solution of our problem as the infinite sum over n of yn times xn. we can write this explicitly as an infinite sum of Cn hyperbolic cosine of k and y plus dn hyperbolic sine of k and y, all of this multiplied by sine k and x. How can we determine Cn and dn? Well, we can use the other two boundary conditions that we haven't used yet. So we have derivative with respect to y of v at x, comma y equal to 0 being fixed as a certain g1, and vy computed at x, comma b being equal to another g2. So what we do is we just compute vy and impose these conditions at specific values of y. This means that our block Cn hyperbolic cosine k and y plus dn hyperbolic sine k and y get fixed to a certain value that depends on Cn and dn. Then we can compute Cn and dn with respect to that. Now that we have the solution for v, we can do the same process for the w. W has now trivial Neumann boundary conditions on the vertical axis. So Vy is equal to 0 at the top and at the bottom of our rectangle, and we have non-trivial boundary conditions in the other two directions. So when we write the Sturm-Liouville problem, we want the Sturm-Liouville problem in the y direction. So when we write the separation of variables, x second divided by x equals minus y second divided by y equal plus or minus k squared, we choose a plus in such a way that when we write the Sturm-Liouville problem for y, we have the right sign in front of k squared. So we have y second plus k squared y equal to 0. Then we solve this. Here I'm multiple times forgetting some solutions. Remember that k squared, you have to justify why k squared is positive. In general, it could be also negative, in which case you would have also to check that the exponential solutions are not fitting our boundary conditions. But we know that, we have covered that multiple times, so I'm not going through those steps here. I just assume that the exponential solutions do not fit our boundary conditions. We need to use our cosine and sine combination. So we can write the solution of y as a cos ky plus b sine ky, so a combo of sine and cosine. And we're imposing the trivial Neumann boundary conditions at the two ends of the rectangle. So we have y prime at 0 equal to 0 and y prime at b equal to 0. So you compute y prime, that is just k times minus a sine ky plus b cos ky, and we compute that at 0. If at 0 y prime is bk, and we want that to be equal to 0, so we either have b equal to 0 or k equal to 0. If k is equal to 0, then y is equal to a, and it does satisfy the boundary conditions. So k squared equal to 0, y equal to 1 is an eigenpair. All the other eigenpairs will have b equal to 0. So y prime computed at b, at small b, only has the sine component. So we have minus a k sin kb equal to 0. We either have k equal to 0 again, or sine kb equal to 0, and then k is n pi divided by b for n equals to 1, 2, and so forth. So we have one set of eigenpairs that is n pi divided by b cos k n y, and one eigenpair that is k equal to 0, y0 equal to y equal to 1. You notice that this k equal to 0, y equal to 1 does fit into our first set if you want to have n starting at 0 instead. So if we add n equal to 0 to our series, then we have all the eigenpairs in just one go. Then now that we have solved for yn, we can solve for xn. Xn has the standard setting of hyperbolic sine plus hyperbolic cosine computed at k and x with some coefficients in front. Then our full solution w is the infinite sum of xn times yn. That is cosine k and y, that is the only part that depends on y, times a linear combination of hyperbolic sine computed at k and x and hyperbolic cosine computed at k and x. And we can determine the coefficients of this sum with the other two boundary conditions that we have in the w case. So the non-trivial boundary conditions are the vertical edges of our rectangle.